Welcome back to TUC lecture series. Today we're going to discuss very important topic of regular language. It's a regular grammar, and it is a most simplest form of grammar, because we're going to see that what special properties or special feature that will be reflected in this regular grammar topic. Before going into the discussion of regular grammar, let's understand what is grammar is. If we talk about our natural language, that is language we usually speak, we use different type of structure like noun, pronoun, verb, something like that. And when we create a sentence, we use subject plus object. So if our sentence do not follow the proper structure of our any language, then that sentence will be meaningless and uninterpretable for anyone who listen to that statement. So the bottom line is we need to follow certain structure, that is certain rules, which will actually construct a meaningful sentence. Same this happens to the grammar we are going to discuss. In this particular topic, we mainly focus on very simple structure of that rules. We usually call it regular grammar. First of all, we will see that a regular grammar consists of 4 parameters. Okay, V stands for the set of variables, T stands for set of terminals, S stands for set of symbols, and P stands for set of production rules. These rules actually guide us that whether particular string belongs to the language of this grammar. We already seen that a language is supported by some machine like DFA or regular expression. Okay, so we always use some sort of this kind of machines or regular expression to determine the structure or to validate any string, whether that string belongs to that language or not. So in this case, we use these 4 parameters to decide whether the language, the string belongs to that language or not. So regular language actually divided into 2 categories. One is called left linear, another call is right linear. In the left linear form, a production is written in this notation. So this is our variable, this is our variable, and x determines the terminal. For example, when we write a string like a b a b, so this is actually a terminal. But if we write something symbol like this, capital letter, always keep in mind that variables always written in capital letters and terminal always written in small letters. So that is the difference we will always see in this type of structure, that is in grammars. So this is a form of linear and left linear and right linear grammar. Now again, a regular grammar may either left linear or be right linear. Any one of these will work. So Another important note is there is only one variable production rule, left or right. So either left or right production rule will be there for any regular grammar. There cannot be both type of uh, linear structure in the production rule, because in that case that the language that it generates will not be regular grammar. Okay, so always keep in mind that grammar, uh, when it is called regular grammar, then it should be left linear or right linear. For example, suppose grammar is defined as set of variable is only one symbol here, that is s. We can also consider variables that when we uh, need to check recursively whether a particular string as a particular symbol of the string actually generated by this grammar, then we recursively use the production rules. So in that case we used to use a variable, so that variable actually considered in this set of variable list, and this is the terminal. When we stop our searching for validation, then we use one of these terminal symbol provided. This is a start symbol and P1 is a production, where P1 actually signifies this set of production rules. So we have here A, B, the terminals, then S, then A. Okay, so if I want to verify that whether the string, suppose W ABA, belongs to this language of LG1, we need to use this production rule step by step. We will see the next topic in this lecture series, that how we are gonna use this production rule to check whether a string belongs to that particular language or not. In the second example, we see there are three variables, S1 is to S3, terminal AB, the start symbol is only S, and P2 is the production, this is P2. So in this case we see this grammar is right linear because the variable is at the rightmost position. In this case is a this should be left linear. The variable is the leftmost position, so this is a left linear. Now come to the important discussion, that when we want to check a particular string belongs to that language generated by this grammar, we actually whatever we adopt, the process is actually termed as derivation. Let's suppose in this example we want to check this string is generated by the language or not, that is example 1. So we tried this first production rule ABS, then again S is replaced by the same production rule to again get ABS. So lastly we stop using this terminal symbol, so this is last symbol. So we can see that using this production rule recursively we can verify whether a string belongs to that particular language generated by this grammar. Now the next step is what kind of operation we can do with this grammar. The most important thing, as we already told, that this is a part of the regular language, then and regular language always associated with some form of machine like DFA or NFA, or combined we can say finite automata, then we can show that obviously there can be some equivalent finite automata for the corresponding regular grammar. So the two operation is to convert this uh, right linear grammar to a finite automata, and then from finite automata to find a right linear grammar. So first we convert a right linear grammar to an NF. It's very simple. We have to see what are the variables, so that we can create a state on the basis of this variable name. So we can see the V0, the start symbol, then we here. Now this terminal is nothing but a transition from V0 to V1. Again we see that V1 to V0 there is a transition, but in this time there are two terminal variables, so we have to choose this path, that is P. Now we can see that in between this V0 and V1 we can put any arbitrary number of states. In that case we can use any name. I have kept it blank because it is not important here, but in that anyone can put any name here. Suppose sorry, any name here, suppose V dash, and then V1 to, there is a transition V1 to final because there is a no state, that is it ends here, that means it indicates a final state. So we have put a transition from with alphabet symbol P to the final state VM. So in this way we can convert a regular grammar to a DFA, NFA, whatever. The next example is of second type, that is a finite automata to a right linear grammar. So what is the problem here? Problem is that the strings that part of the language follows these rules, like number of A in the strings plus number of B times 3 is always even. That is, if number of A is 2 and number of B is also 2, then we have 6. So you can see this is even. So we have to find those strings where number of A's and number of B's times 3 is even. So there are 4 cases we can consider here. The first case where number of A, number of B both odd. Sorry. Odd, not odd, even. Okay. So we can say that number of A and B are twice n type. So we have twice n plus 6n, that is even. So it is satisfied. In the case 2, both are odd. So twice n plus 6 and 3, that is 8, 10 and plus 4. So that is also even. Here condition satisfied. In the case 3, we see one is odd, another is even. So it twice plus 1 plus 6, and this is obviously odd. The second case, twice n, that is number of B is odd, then 6n plus 3, that is obviously odd. So these two condition does not hold. So we have to take either n A or n B both odd or even. So there are, if both are odd, so in that case we put a NFA like or DFA like this, and then for even we put like this. Okay. Now look at this for odd number of A and B case. So first of all, see what is the minimum number of transition and what are the symbols found in these transitions are, that is, if we take B, if we take this path, then B, then A, then it goes to final state, that is the minimum terminal string BA. Now if we follow this path, then first A, then B, then AB. So we put AB, AB and BA. Now if we want to repeat it again, so you have to follow we have to go to the start state again. So if you follow this path, then BA, BA. So you have put BA, BA. If you follow this path, then AB, AB, AB and AB. Okay. So we put, so this is for the odd case. For the even case, this state accepts without taking any input, so lambda is included. Then BA, BA, because we have to go to the final state from the starting state, the full path. Then if you follow this path, BA, BA, if you follow this path, we follow AB, AB, so this portion also included. Now finally, when we want to stop, we replace S with lambda. So in both the cases, we actually find our desired regular grammar for the said problem. And now if we march to this like this, the single grammar production rule, then obviously can say this include both the odd or even condition. So this is the way we actually can convert from a regular grammar to NFA, FA, or a finite state automata to regular grammar. So thank you.